Okay. Very good. So let's go ahead and get started. So by way of introduction, I'll introduce myself. My name is Jonah Canner. I work here at Caltech on the Gravitational Wave Open Science Center. What we're here today for are lectures for the 5th Gravitational Wave Open Data Workshop. We've got 2 speakers today, Martine Beroiz and Jenne Driggers. And these lectures are going to be broadcast over YouTube live stream and recorded so that they'll be available for folks to watch both during and after the lectures. After those 2 lectures, I'll take just a few minutes to introduce the tutorials and the activities that we'll be doing, that many of us will be doing later today or even tomorrow morning. In general, the workshop combines 2 main elements. We'll have these online lectures, which are on Zoom. So if you're listening right now, you've already figured out how to do that. And then we'll also have an online course, which is going to be through the Thinkific platform. And that online course will walk you through a number of software exercises and tutorials, quiz questions, and a data challenge so that you'll have an opportunity to try working with gravitational wave data yourself. And I'll show a few of those elements after the lectures today. While our folks are speaking, there's 2 ways to ask questions. We can use the Zoom chat, that's fine. We also have a topic posted on ask.igwin.org for the day 1 lectures, and we'll also invite you to post questions there. And our mentors will do our best to reply to questions that go into both places. Okay, so I think with that, we'll go ahead and get started. Our first speaker today is Martine Burrowis. Martine is a staff scientist here at LIGO Laboratory, and he's going to introduce us to public LIGO data.
Thank you. Let me share my screen. I hope you can see my slides now. So, well, thank you for the introduction. Let's talk today about the what type of data you can find among the publicly released gravitational wave data. So, yeah, my name is Martin. I work at the Gravitational Wave Open Science Center, and basically what we do at WASC is release, archive, and serve gravitational wave data to the scientific community and the public in general. We offer a catalog of events with parameter estimations, posterior samples, strain data, and basically data quality flag segments. I'm going to talk about all of this in the next future slides. And we also provide information and tools and software to understand and use the data, like tutorials, interactive web apps. We have web API, documentation, that kind of things. So I encourage you to go to our website, wasc.org, and explore all of the things that we have to offer. This is currently the detectors for which we have data. There are, because you know, there's 2 main ground-based observatories in the United States. One in Hanford, Washington, the other in Livingston, Louisiana. This comprises the LIGO detector set. And there's a few others in Europe, Virgo in Italy, and Geo 600 in Germany. And now we have Kagra in Japan as well. We have data for all of this. So if you're interested in getting data of any of these detectors, you can find them at wasc.org. This is a brief summary of how the number of detections through the years. We have the first observing run, 01, that detected the first 3 gravitational wave. This is the first run that actually detected events, gravitational wave events. And then on the second run, 02, 8 more events were detected. There's a big jump in the number of detections by an order of magnitude in O3. We have on the first half of O3, 44 events were detected, and for O3B, another 35. So we expect to have to find even more in next observation runs. So we have now a grand total of 90 events, 90 confident events in the gravitational wave transient catalog. There are a few other marginal events, which is just not as confident as the confident events. So we have over 90 events total in our website. And yep, this is our website, the Gravitational Wave Open Science Center. And you will interact with this website mainly through the menu bar here at the top. Today, I'm gonna focus mostly on this first menu item in the data, because this is where you will find most of our data, right there. So let's begin with strain data. Strain data, as you may know, is basically the main product, the main data product of an observatory. It's also known as H of T, or the differential arm length of the interferometers. And this is the main time series that you will use to analyze for gravitational wave events. So where can you find it? Well, it's there in the first item. If you click there, it will take you to a page where you can find all of the different releases, public releases of data. Public releases usually are basically two kinds. You can roughly say there are two kinds of public releases. Sometimes during an observation run, there's a detection of an event, and it is published and made public during the event, during the run. So this is basically detected by the low latency group, and it is released early, early meaning before the bulk data, in the event portal. So there you can find a specific strain data and segments for that event. And the other type of event, the other type of release, public release, is basically done at the end of an observing run, and that is the whole bulk data of the whole run for all the strain data for all times, whether there's a detection there or not. And this bulk data is released in 4 kilohertz and 16 kilohertz sampling rate, and along with documentation and the segment information. But like I said, this is typically done at the end of an observing run. And here on the left, there's examples of past data releases, and you can see that you can get all of those in this page. If you're going to work with all of the data, we recommend that you do the download through something called the CVMFS, which is basically like a distributed file system developed by CERN to replicate the data, remote data, to replicate it locally on your computer. And you can use this one to basically download the whole data that we have to offer, if that's what you need. And there's also other, you can use NDS2 that you can find out more about in our website, or you can use dedicated software like GWPy. So yeah, those are the ways to download data. And if you're not interested in the strain time series itself, and you're more interested in the individual event or a catalog, or then you can also find that. We offer that through this menu item here in a second item, and it will take you to the event portal. In the event portal, basically the main one catalog that you definitely will want to check is the GWTC, the Gravitational Wave Transient Catalog. This is like a curated list of all the events that we are finding with the latest parameter estimations. But you can also find other releases, past releases, or a full list of all of the events with all of the versions, or query your own search for specific cases. So I'm going to go through all of these elements. Let's first check out these releases. You click there, you take to the release list page. And here you can see a list of all of the past releases. And basically, a catalog or a release is a collection of events with parameter estimations. Like I said, the one that you kind of probably want to check out first is the GWTC. But there are like children, you could say children catalogs for GWTC. You have the GWTC1, which corresponds to for 01 and 02 only. Then the GWTC2 for 03A run, GWTC3, 03B run, and there are others like GWTC 2.1. You can find them all in the release list in the event portal of our website. And this may have confident detections or marginal detections, or a mix of both. And if you don't know exactly what they contain, well, here you have a description for each one of the releases and the corresponding publication whenever there is one. So that's all for catalogs. Here in the events, this is basically a list of all of the different events and all of the different versions that we have. And if you click here, it's going to take you to a list view of the events. The first thing you'll find in these lists are the name, the version, what release it belongs to, and a few parameters like the GPS time of the detection and the masses, etc. If you click on this little arrow, it will give you more options to display parameters. So don't miss on that one. We have more parameters than the ones that you originally see. So all of these parameters are parameters of the merger, and you can check them all out to see them. And this is the list view. If you click on any one of these events, it will take you to the detail page. So in the detail page, you can see events isolated with more detail. And the first thing I want to point out is that you may find out that their events have versions. So you may ask, well, isn't it an event a single detection, single point in time? And yes, it is. An event is just one. But what happens is that the event or the strain data is reanalyzed many times, and every time we analyze the data, instead of replacing, for example, we analyze a chunk of data and we do estimate the parameters of the merger. Instead of replacing the parameter values of this event, we create a new version and we keep the previous values in a previous version. So that's why these events sometimes can contain up to 4 different versions. That's because it's been reanalyzed several times. And this could be for many reasons. Typically, you have different calibration on the strain data because you find a better cleaning technique to denoise the data. You may have different analysis result or a new publication that publishes new parameter estimations, for example. So each one of these will produce a new version of the event. This has the advantage that if you wrote a paper with a specific event version, then you can refer it to it directly, and it will not change. Typically, each version corresponds to a different catalog. That's basically the catalog or publication. That's typically the case. Another thing you can find here in the detail page are links to the Grace DB. If you don't know, Grace, the low latency group basically uses the Grace DB as every time it detects an event, it will issue an alert, typically to observatories that are interested in doing electromagnetic follow-up for these events. And it published this detection trigger on the GraceDB website with some preliminary parameter estimation of some parameters like the masses and the localization error, expressed in a sky map. So this, if you haven't checked out, you should keep this website in mind, GraceDB, and you can find links for each one of the events there in the detail page. These triggers basically come before the publication on WASC. So the timeline is basically, it's first detected by the low latency group, published on GraceDB, and then this is basically of an online type of analysis. Then it's revisited offline, and if it turns out that it's an actual gravitational wave event, then it goes into WASC. So it will appear first on GraceDB, but then you can refer back through these links. So that's for GraceDB. And another thing you can find here in the detail page is the many pipelines. LIGO has many detection pipelines, or I should say LVK has many detection pipelines. Here's an example for a pipeline for PyCVC, that's a search pipeline, or GSTLAL, and each one of them publishes detection parameters that are not always the same, but usually there's one that is the preferred one or the default. And you can check them all here. And sometimes some of the pipelines will produce, will contain links that will go into Zenodo. Zenodo is like a type of archive website. And from there, you can find links to download the posterior samples or sky maps for these events. Not all of the events have them, but some of them will, and you should check if there's any there. That's for the pipelines. Oh, I'm gonna talk about segments later on, but for now, I would like to point out that you can query for segments from the detail page as well. And that will take you to a page where you can find data quality segment flags for the event, for the particular event that is displayed here. And yeah, just so you know that you can actually query for segments for a particular event through the event portal. But I will talk about this later on. And finally, you can also download the strain. This is not a bulk data strain, but it's just the strain around the event. And you can preview there with the Q-transform how it looks like in frequency. Or download the strain files directly in different formats. You have gravitational wave frames or HTF or just simple ASCII plain TXT files. And you can find it in 4 kilohertz sampling rate or 16 kilohertz and in 32-second window or 4,000-second window around the event. So plenty of different options depending on your needs. And lastly, on the event portal, we have this handy query form in which if you have a specific type of search that you're interested in, that you want to constrain the parameters somehow, you can do it through this query page. Basically, for example, if you're interested in mergers that have the secondary mass less than 5 solar masses, and you want to restrict all of the events for that particular constraint you have in mind, then you can use the query page there. You can constrain pretty much every parameter that is on the event list tables. You can constrain it here, or you can also constrain on dates. If you're interested in a period of time, detections during a time window, you can do so too. And the output could be HTML, JSON, CSV, or ASCII. So yeah, please check that out as well. Next topic, timelines. The timelines app, you can find it here, third item, the data menu. And basically it's an app, we'll take you to this page. It's an app to query for segment data. So on this one, you can just choose a run and a GPS interval. If you don't, the GPS interval is in principle fixed to the whole duration of the run. But if you want to restrict it more, you can change as well the GPS interval. And then once you fix the time interval you're interested in, you can either download string data for each one of the observatories that were active at that time, or you can download a list of segments in JSON format or ASCII format. Or if you're not interested in the actual numbers, but you want to just visualize how they look like in the timeline, then you can use this plot thing. You just have to select the segment, the type of segment that you're interested in. Click on that display button, and we'll take you to this page where you can visualize better the segments. Basically, a segment is a on-off type of time series. It tells you, depending on the segment, it will give you different information, but the segments that are related to data quality basically tells you when data is usable or not, or not. This is basically the quality of this string. So why would a piece of data not be useful? Well, there are many reasons. For example, there could be excess environmental noise, angular misalignment of the test masses. You may have saturated photodiodes and many other countless glitches. And each one of these will flag the strain data, so you can avoid that specific segment. These are basically the CAT1, CAT2, etc. Type of segments. There are also other type of segments that deal with hardware injections that you also may want to check that out. This is, for example, an example. This is an example of Geo and Kagra. These are 6 segments, and some of them are CAT1. This is data quality, and some others are hardware injections. So yeah, these hardware injections are intentionally added to measure things like false alarms rate or detection rates, for example. So yeah, this is how you query for segments. And lastly, I would like to talk about the web API. So far, everything I have talked about before mainly focus on the HTML part of the website, the face that you see in a web browser. But if you're doing more programmatic things, you may want to interact with the website through the API. This is basically for here. You can find the API documentation in software page in the software section. We'll take you to this page. And basically the API, you communicate all of these different data products that I talked about, you can find in the JSON format through all of these URL nodes. There's a long list of nodes.
I'm sorry, Martin, you've been muted. If you could unmute yourself, I'd appreciate it. That was my fault. Sorry for the trouble.
No problem.
Maybe back, say 1 minute or 30 seconds.
Oh, I see. No, yeah. So I was talking about the web API. On the web API, maybe you want to interact with the website not through the HTML pages, but through our API that returns the information in JSON format, which is more convenient to work if you're from a script, for example, and to parse the data. All of the data products that I mentioned before, like the event catalogs, the strain data, well, not those, yeah, the segments, all of that is available through a JSON API, which is more convenient for, like I said, working programmatically through scripts. There is, though, a Python client that you may want to use instead of yourself writing your own client. If you're working on Python, you definitely should check the WASC Python client. You can, of course, also interact with it using curl, for example, or JavaScript. But if you're using Python, we have another way that you can just pip install WASC. That's the name of the client. Or you can read the documentation through our WASC client at git.org/wasc/client. And there's also another way to do it through a Python library called gwpy. And I believe that you are going to learn how to use both of these clients or software in the hands-on session. So yeah, you can learn about that then. And this is all I want to say. So thank you very much.
Okay, perfect. Martin, thank you so much for that presentation. We really appreciate it. So I've seen lots of questions go by in the chat, but we do have a few minutes for question and answer now. So I'd say if you'd like to ask a question, please go ahead and use the raise hand feature on Zoom, and our team can take questions if there are any. Going once? Going twice?
I would like to make a question, Luis from Mexico.
Hi, Luis.
I would like to know more about the CERN contribution to our database. The CERN contribution to our database, Martin.
Yeah, CERN is not actually contributing to LIGO specifically. It's just a piece of software that they developed to distribute the files. It's called the CVMFS, but we don't use any of their data. It's just the software to basically that you can use to replicate the gravitational wave data locally on your computer. So yeah, that's why we use it.
Okay, thanks.
Okay.
Great.
Okay, perfect. Thank you, Luis. Any other questions for Martin? Okay, very good. Well, thank you again, Martine, and thank you for, I see a lot of questions, good questions and good answers in the chat. So thank you for the many good questions. Also, thank you to our mentors for the many good answers. I should say that we're lucky this morning. These workshops work because we have a number of mentors who essentially volunteer their time to support these workshops. A number of them are online right now. These mentors are going to, throughout the course of the workshop. So first of all, they've done a lot of work to prepare the tutorials and the online course, and we're grateful for all of their work. In addition, our expert mentors are going to be available to answer questions via our discussion forum at ask.igwin.org. So of course, if you're on Zoom, you're welcome to use the chat. If you're not on Zoom, or if you're watching this as a recording, you are welcome to post questions in our discussion forum at ask.igwin.org, and our mentors will do their best to monitor that discussion forum and answer questions as they arise. So thank you all for the good discussion and good attention during Martine's presentation. Okay, so I think with that, we can transition to our next speaker. I do see that Jenne Driggers has been able to join us, and she's got her slides shared, which is great. Jenne is a staff scientist with LIGO Laboratory. She's works at the LIGO Hanford Observatory in Washington State, America. Hi, Jenne, nice to see you. Good morning.
Hello, I hope you can hear me okay.
Yes, you are clear, and you're welcome to start whenever you're ready.
Thank you for inviting me to come share some of what I do and my love for the gravitational wave interferometers with all of you. Martine just shared with us how you can access and utilize the open data from the gravitational wave interferometers around the world. I will share with you a little bit about where did that data come from and how do we create that data? How do we know what kinds of signals may be in that data in terms of amplitude and phase, and what do we know about that data? So first of all, there are many interferometers around the world, and I hope that this is not new information, but it's very exciting that we have several world-class gravitational wave interferometers around the world. I work at the LIGO Hanford Observatory here in Washington State in America, in the United States of America. We have a second interferometer that we operate in Louisiana in the United States of America, and these two detectors are very similar to each other in terms of technology. We also work closely with the Virgo interferometer just outside of Pisa in Italy, as well as closely with colleagues from the Kagra interferometer in Japan, which here you can notice that this is, rather than a true photo, this is rendering because the Kagra interferometer is underground to help isolate from seismic motion. So they've implemented their technology underground to get advantages from being away from the Earth's surface. And we're also very excited that in the coming years, we will have yet another ground-based interferometer, LIGO India, and they should be coming online, hopefully in the next some number of years. After that, there are other future detectors which are in planning stages and proposal stages, but these are the interferometers that are kilometer scale baseline for these arms that are currently operating or very, very soon to be operating. I say kilometer scale because these are small photos, and for that I apologize, but this is a building. You can't even see the cars parked at the building, and the arm length is 4 kilometers into the distance from the main building. So these are really truly large scale detectors to provide the data that Martine was just telling us about. So I'll talk a little bit about how do we use these machines to measure gravitational waves from astrophysical events, and touch very briefly on how do we calibrate them so that we know what amplitude, what signals we are seeing should we see a signal. So first of all, very, very briefly, gravitational waves are ripples in space-time. They're affecting space-time itself. So in the upper corner, I have this simulation of two black holes inspiraling around each other, and they're about to merge into a single final black hole. As they spiral around each other, space-time, they're emitting gravitational waves, and space-time is stretching and squishing as the gravitational wave travels along this blue tube. And LIGO and our colleague interferometers measure these distortions of space-time itself. So if we think about in just a different plane, a different dimension, we have our blue tube of space-time that will stretch and shrink as a gravitational wave passes through the plane of the screen. We can think to put a laser and a beam splitter in the center of, not necessarily in the center of, but somewhere in space-time. And then as the gravitational wave passes through the plane of the screen and space-time stretches and squishes along these axes, this will move these mirrors because these mirrors exist within space-time. And using this laser that we can send and split the beam in half, 50% will go one way and 50% will go the other way. And then as these mirrors move, it will create an interference pattern here at the beam splitter. The light will recombine and go towards a photodiode. And on this photodiode, we will measure how much light is here. And that tells us about the interference pattern, which holds information about how space-time is changing, how space-time is moving. So here I've got a video showing that again. Here's a laser, a beam splitter, and the light goes to the end stations, the end mirrors. And then if a gravitational wave passes through this little interferometer, the mirrors move. So here we've got the light, and the light is represented as a sine wave. It reflects off of the end mirror and also the other end mirror. And as the light is recombined at that beam splitter, it happens that here there's no light. They've interfered deconstructively. But as the end mirrors move, it changes the interference pattern of these two sine waves, and we see more or less light on that photodetector. So this is how the photodetector signal can tell us about how much light is here, and which then tells us about how these mirrors were moving. And since those mirrors exist in space-time, how space-time was changing with time. So that was a very basic Michelson type interferometer. And that is indeed what our gravitational wave detectors are based upon. However, we have many, many extra components which we use to allow for much more sensitive detection of the gravitational wave signals. So here in this cartoon, I've got my main laser. We've got several subsystems to stabilize that laser in frequency and intensity, because the laser is the ruler with which we are measuring how much the mirrors are moving. So the laser needs to be very, very stable. And so we use several subsystems to stabilize that laser. We then send the laser light into the main interferometer, and we have that same beam splitter that provides that same function to split the light, half going to one arm cavity, half going to the other. And then the light is allowed to recombine, come towards the output of the detector. The light is cleaned up a little bit more with yet another subsystem. And we finally go to the actual gravitational wave detection photodiode detection port. All of these other mirrors, in addition to allowing for some steering that is kind of indicated here, allow for us to increase the amount of laser power that is contained in the interferometers. So these represent our 4-kilometer arm cavities, and we can use them to build up the laser light more and more and more. And this improves our sensitivity at higher frequencies by having more and more laser light that is present to measure the motion of these mirrors. Due to conservation of energy, any light that did not, when we have our interference at the beam splitter, if we have deconstructive interference here going towards our gravitational wave port, that must mean that we have constructive interference and lots of laser power traveling back towards the main laser. And one way that we can think about this is light that did not detect a gravitational wave signal. And so we put in a recycling mirror to turn that light around and have it go back into the main interferometer and try again to measure gravitational waves. So this, in effect, allows us to build up our laser power even further, because the main laser, while we do have phenomenally exquisite lasers, there is a limit to how powerful of a laser can be made at the stability that we need. And so we utilize these other techniques to build up the laser power in the interferometer to improve our sensitivity at high frequency. The other big extra component here is a signal extraction mirror. And this mirror is used really to adjust the frequency dependence of our ability to detect the gravitational waves. This allows us to detect gravitational waves over a more broad frequency so that we'll be able to see more components of the astrophysical signal. And you'll hear more about the astrophysical signals themselves later. But this allows us to tune what frequencies we are sensitive to. I like to show this photo. This is our instrument hall at the LIGO Hanford Observatory. Just to give you a scale of, those were cartoons. This is the real detector, and this is the detector that I work at. And so this is the actual hardware that we utilize to detect gravitational waves and send the data out to places like the Open Science Center. And here I overlay a cartoon of our main laser is in this corner of the room. We've got our main beam splitter not so far from the laser. The beam splitter indeed splits the light about half and half, going through to these arm cavities. And it's difficult to see in this photo, but the laser beam is traveling through the vacuum tube and out into, continues out in the vacuum tube, out for 4 kilometers before it hits the end mirror, reflects back, and comes towards the main hall again, hits the beam splitter to recombine, and then finally we'll go to the gravitational wave photodetector here in this corner of the room. So why do we do all of this, and why do we work so hard to put all of this hardware together to detect the gravitational waves? It's not trivial. It's really very, very difficult to measure something at this small of a level. So this plot I show, there's no data here yet, just so that we can talk for a moment about what it will show. On my x-axis, I have frequency. So I know that there's been some chat in the chat window during Martine's presentation about what kinds of FFTs and stuff we can use. So that's one thing we do when we're looking at the noise performance of our interferometer. We do an FFT to using the Welch's method to look and see what amplitude of data we have at each frequency. So we usually look between about 10 hertz and a few kilohertz. And the signal that I'm interested in usually is how much are our mirrors moving? How many meters are we sensitive to? How many meters of motion are we sensitive to? And these are 10 to the minus 15, 16, all the way down to 10 to the minus 20. And just for some sense of scale, the diameter of a proton is about here at the top of the plot. So we're measuring things that are much more sensitive, much smaller size scale than the diameter of a proton by orders of magnitude, factors of 10. So this is an image of some of our data from, this happens to be 2019 data during our third observing run. And it shows many different traces, but in particular, the purple line is the design sensitivity of the gravitational wave detector. So how sensitive we think that our hardware can enable us to detect gravitational waves. And these other traces in red, yellow, and blue are the sensitivity of the actual gravitational wave detectors at some point in time. The blue is the Louisiana detector, and the red and yellow are two different points in time of the Hanford interferometer. And you can see that particularly above 100 hertz, we are impressively close to where our design sensitivity is. So we do a nice job of achieving the sensitivity that we think that the hardware can give us. And so this says that this is kind of our baseline noise level. So should a gravitational wave come through our detector, as long as the effect it has on the mirrors is larger than this many meters of motion at each given frequency that the gravitational wave signal is at as it moves through time, we should be able to detect that gravitational wave as long as it's larger than our baseline noise. And how high above the baseline noise the signal is can give us information about how well we are able to measure that signal. And obviously we would like to improve and lower our baseline noise sensitivity so that we can continue to measure gravitational waves with higher and higher fidelity. This is just another way of thinking about, just to really clarify, because it's such an impressively small number that we're measuring for the distance of the meters. And because what really matters is not the individual motion of a mirror, but the motion of the mirror divided by the beamline that it is looking at. So for LIGO, it's 4,000 meters, 4 kilometers. So our mirrors move on the order 10 to the minus 19 meters, and that is divided by 4,000 meters, because that's the gravitational wave strain that matters for measuring the gravitational wave signal. How much the mirrors move divided by the total baseline. And that's equivalent to measuring, again, this is a ratio, the width of a human hair, level of precision, the distance between the sun and the next star. So that's how very, very precise the gravitational wave interferometers are. There are many reasons why we are and are not able to measure more sensitively at different frequencies. And this is a plot showing some of the contributions to the sensitivity. This is a really complicated plot, so I'll just touch over it a little bit briefly. In red on this trace, we have the actual measured sensitivity of one of the gravitational wave interferometers. And in dashed line, we have what we think that we should be able to achieve once we are completely done with our next several years of installation of hardware and software and other technologies. Importantly, this includes much higher laser powers than we have had in the past. The rest of these traces show the limits to why is this red trace not better. And so one of the big limitations in this light blue trace is the quantum noise due to the quantum shot noise. And that's related to the amount of laser power that we have available to be measuring the gravitational waves and to be illuminating those photodiodes to show that we can actually measure the voltage of that photodiode. So you can see that with our current laser powers, we are limited at this level. And so that's why we're not measuring better. So we know that should we be able to improve our quantum shot noise here at high frequencies, we can allow ourselves to measure more sensitively at these frequencies. At lower frequencies, there's a different quantum effect, which is quantum radiation pressure, that we'll talk about in a little bit in more detail. And that is a limit to what we expect that we are able to do eventually. The design sensitivity, it's a limit to the design sensitivity in the dashed curve, but that's not actually the most important noise source that contaminates our gravitational wave signal. Our most important noise source right now is controls noise, which is shown in this dark purple curve. So, and that is because in order to actually keep all of this laser power circulating in the interferometer, we need to keep our laser beam pointed so that it matches the alignment of the mirrors and that the mirrors are well aligned to each other and that laser beam. We also require, in order to build up interference inside the interferometer to build up the laser power higher and higher, that mirrors are held at an integer number of half wavelengths apart. So we have to hold our mirrors a precise distance apart as well as a precise alignment. And to do that, we need to push on the mirrors to hold them still where we want them to be. And that all adds up to contribute to this controls noise. And so we hope that as we improve our controls loops and other technologies, we can lower this noise and bring it closer to the design sensitivity. And that will enable us to have better measurements of gravitational waves at these lower frequencies. So I've told you about the sensitivity of our gravitational wave detectors, but how do we really know how much our mirrors are moving? We have to know somehow at some precise level in order to be assured that we're sharing data that we're confident what the data means. And the main way that we calibrate our interferometer and the motion of the mirrors is with photons themselves. So we have an auxiliary laser, an extra laser. This is a cartoon of the end mirror. So this interferometer beam comes from off the screen, the main beam splitter, and it has traveled 4 kilometers to our end mirror. And a few meters away from the end mirror, we shine an extra laser at the mirror. And because the laser light carries momentum, this laser beam, as we shine light onto the mirror, it imparts momentum and causes the mirror to move. And the force that is applied to this mirror is related to the power of our extra laser divided by the speed of light. And there's a factor of 2 because we've reflected off of the mirror. So in order to do this reflection, to get the light to reflect off, to change directions, we had to impart momentum onto the mirror itself. And so equal and opposite reactions, if this laser light bounced off of the mirror had to react and move. And this is related to our radiation pressure. This is a type of radiation pressure. But here we have a very, very extremely well calibrated laser from our National Metrology Institute here in the United States is NIST. So they have told us with very exquisite precision how powerful is this laser and what is the amplitude of this laser light. So we know very, very precisely how many photons we are hitting our mirror with. So we know very precisely what force we are applying to our mirror. And since we then know how our mirrors respond to the forces, then we can know how much the mirror must have moved due to this light from the extra laser beam. Something that I've glossed over, but I'll come back to now very briefly, is that our mirrors, because we want them to exist and kind of float in space-time, but we are a ground-based machine and so have to live in a world of gravity. What we've chosen to do is we suspend our mirrors as a pendulum. And so we know how that pendulum responds to the forces applied, such as this extra laser beam. And so since we know what our pendulum will do as a function of frequency when force is applied, then we can know how much did the test mass, which is what we call our mirrors, it's a test mass existing in space-time, how much did it move due to this auxiliary laser? And then we can make sure that the data we send out from, because then this motion of the mirror affects the main interferometer beam and will show up in the data at our gravitational wave detection port. And we make sure that the data that comes out our gravitational wave detection port matches very well the motion, the meters of motion that we have imprinted, that we have put onto the laser beam, by having moved this mirror. We don't care so much just at DC, at low frequency, like extremely low frequency, like 0 hertz, just by pushing. We don't care so much about the calibration at that low of a frequency because we are on the ground and we have seismic motion and we can't detect gravitational waves with excellent ability at infinitely low frequency. But what we do care about is the data and the calibration of the data above a few hertz and up to a kilohertz and beyond. So what we can do is we can modulate the power of this auxiliary laser. So we can have it be more laser power, less laser power, more laser power, less laser power. And we can do that at a frequency that we choose. And then that moves this mirror at that frequency by a known amount. And so we can compare as a function of frequency, our calibration of this, of what we know the mirror is moving to the data stream. So something to note is that we always have calibration lines present in our observational data to monitor as a function of time the accuracy of our calibration and to monitor should anything change about the whole interferometer, we can know that nearly instantaneously, and we can correct for that. During maintenance periods of the order once per week, we take a much more detailed calibration measurement at many more frequencies to be assured that our full calibration is as accurate as possible. When we calibrate, of course, we say that we know very, very well what the amplitude and frequency of our mirror motion is, the data to mirror motion. But there is, of course, a limit to how well we can know. And the systematic error reports how well do we know our calibration and how well can we truly say we know our mirrors are moving based on our data. So these plots are as a function of frequency, starting at 10 hertz, going up to 5 kilohertz. This is the amplitude of the signal, and it is a ratio of a measured, using those laser calibrators, measured response of the mirror motion to an expectation of what our current or previous calibration was. And then we divide by 1 so that this is a percent error from what we thought we had. So we measure it sometime and compare to what we thought we had. And within a 68% credible level, for the most part, particularly where the gravitational wave merger happens and some of the ring down, we are much better than 2.5% error. So we can say that we know our calibration to better than 2.5%. And similarly, we also care about the phase of the data, because the phase of the data also can help tell information about the object that created the gravitational wave signal. And so this is, as a function of phase, what is the difference between our measurement and our calibrated, like what we thought the calibration was. And again, you can see that it's very, very exquisitely small, that we know very, very well how well we understand our calibration. These calibration uncertainties are folded in when we do analysis of our data to try and understand the astrophysical parameters of objects that created a gravitational wave source. For example, the masses of the black holes or neutron stars or whatever other object, how far away that gravitational wave source is, and other parameters. Our uncertainty in being able to say what those parameters are, part of that comes from this calibration uncertainty of how well are we able to calibrate the data that comes out of the interferometer itself. As a final thought, I'll share with you our kind of history of improvements in that sensitivity as a function of time and where we think that we can go in the future. So I hope you know that we've had 3 very successful observing runs so far, which we call observing run 1, observing run 2, and observing run 3, 01, 02, and 03. And the gray, yellow, and red traces are measured data, measured sensitivity from those 3 observing runs. And you can see that we've kind of slowly made progress between our first and second observing runs. Our third observing run, we were able to do much better. And as we go forward, we hope to be able to achieve our design sensitivity of the originally envisioned hardware in the black trace. And even further, we are planning, designing, and already starting to install technologies to enable us in our current facilities to go even farther to hopefully achieve this green dashed line of sensitivity. So over the next few years, we will continue making improvements to the detectors to further improve the quality of the data that we send out to the Open Science Center. And with that, I'm delighted to take questions. I'm sure it looks like there's been a lot of chat, and hopefully our mentors from various sites have been able to answer some questions, but I'm also happy to take further questions.
Excellent. Jenny, thank you so much for that great talk. Okay, yeah, there has been a very busy chat, but let's see if anyone would like to put their hand up and ask a question now. All right, Manuel.
Hello, hello. Thank you for the presentation, very interesting. And I have a couple of questions. So my first question is related to an old feature that I found in data, and today is not more anymore. It's about the hardware injection. What is the reason to perform less or none of hardware injection? This is my first question. My second question is about the futures about detection. What about the detection about unmodeled waveform? I think maybe in the next 10 years we are able to detect a galactic waveform for a supernova, but how long time we need to wait to do this detection more frequently? So this is my two questions. Thank you.
Thank you. Those are both excellent questions. Your first question about hardware detections, that's a very good question. We did indeed used to perform hardware injections, which is what we call the addition of simulated gravitational wave signals into the detector itself. And we would do that by pushing on the mirrors to simulate a gravitational wave. And then we would look for that simulated gravitational wave in our photodetectors and our gravitational wave data. We used to do this much more during initial LIGO, where initial LIGO finished in 2010 or so before we went offline for major upgrades to our current generation of facilities, advanced LIGO. And the biggest reason that we've kind of stopped doing that is we know that we are able to successfully detect gravitational waves.
Para pedir la palabra, ¿qué hago, Peter?
And so since we know that we are able to successfully detect gravitational waves, it's less important to us to put in those hardware injections. And part of that is that any time that we are almost polluting the data with hardware injections, that's time that we would have to do work to remove that simulated signal before we can really look carefully for any true astrophysical signals. And that is work that we know that we no longer need to do because we've been so successful detecting gravitational waves. So something that we do a lot of, although may not be exposed to the Open Science Center, is we put, and so this is something you can also do for yourself, and I hope that you do try, is you can put in a data simulated gravitational wave signal by just summing in a simulated gravitational wave signal into some part of data. And then you can use detection tools to try and look for that software simulated data. And that's how we're now doing most of our testing of our detection pipelines, is by using software simulated data. Unmodeled searches, for your second question, another excellent question. There are data pipelines that do look for unmodeled gravitational wave sources. So something that I didn't talk about is how we look at the data from our multiple sites. And what these data pipelines for the unmodeled searches do at kind of their basic level is they look for some kind of energy or signal that may be coherent in all of, or at least more than one interferometer. So unmodeled gravitational wave sources, I don't think we can detect with just a single interferometer, because it would be very difficult to distinguish that from some noise due to the facility or due to the hardware. But if we saw the exact same signal in multiple detectors, then we could start to look and examine the data and say, is that something of interest? And I think those searches will be much easier as we improve the noise, as we lower the noise, then any potential gravitational waves will be more clear, even if they are of that unmodeled type. And further details on that, I'll leave. I know that you've got several other talks throughout the week that will go into more of those kinds of details, but thank you for your questions.
Okay, thank you. Thank you.
Okay, perfect. Thank you so much. Looks like our next question is from Sade.
Can you hear me, sir?
Yes.
Thank you very much, Dr. Driggers. I have one question. How the observatories can distinguish the real gravitational wave from the external noise and waves on the different frequencies which are created on the Earth or out of the Earth and comes from, for example, our solar system? How we can distinguish in our observatory?
Very good question, and very important question. And a lot of that, the answer to that question, the result of the answer to that question is exposed in the Open Science Center as part of our detector characterization flags. So that's how an external user of our data can see what we have determined about the external noise sources. But what we do is we provide, one final gravitational wave signal data stream, but we have something like 250 or 300,000 other channels of data that we look at, most in an automated way, because one person can't look at 300,000 channels of data. But those include seismometers on the ground, measuring ground motion. Those include magnetometers to measure, is there some stray magnetic field around? They include, we have cosmic ray detectors, just in case we have a cosmic ray storm that is affecting the detector and the data in some way. And so by comparing all of these other auxiliary data channels to our main gravitational wave channel, if we see some signal that looks unusual in our gravitational wave channel, but we also see it in one of these auxiliary channels, we know that these auxiliary channels cannot detect gravitational waves. If they could, we would use them instead, and we wouldn't bother to make a whole facility such as this. So if we see in one of our auxiliary channels some signal that looks just the same as the unusual signal in our gravitational wave channel, then we can say this must have been caused by some kind of thing that's not astrophysical, whether it was ground motion or magnetic field or wind traveling, air currents blowing on the buildings, any number of different hardware glitches, a computer pushed on a mirror more than it was supposed to. We can know that because we know what our computers are doing. And then that information is all encapsulated and summed up in our data quality flags. that indicate when is the data sufficiently high quality that it is worth looking for gravitational wave signals. If there are other things from cosmic sources or non-Earth sources like the solar system, that's a really interesting question. And I guess my first thought is that if it's caused by some gravitational wave thing, some kind of gravitational effect, then that's interesting. And that becomes a signal for us that we want to investigate and look at. And perhaps it would not be a binary in spiral, but it would be one of these unmodeled type sources. That said, because the stretching of space-time effect is very, very, very small, it's really difficult for anything to be conceivable that it would make an effect that we can measure, that we are capable of measuring, unless it is from something that is very, very massive, like a black hole or a neutron star, or some truly exceptional event like a supernova explosion. So there's some unlikelihood that there would be something in our solar system that would make an effect that we would detect in a gravitational wave way, just because it would be so very, very small. And our hardware detectors are not yet exquisite enough to see that level of signal. But thank you.
Thank you very much. Thank you very much.
Okay.
I have a question.
Yes, Luis, please go ahead.
Doctor, if the Fabry-Perot arm's length increased by a factor of 100, what happened with its sensitivity? In which factor does it increase?
Yes, that's a very good question. Thank you. So because what matters, the truly astrophysical signal that we're looking for is the strain, which is the motion of the space-time stretching divided by the distance over which you measure. If we were to increase the length of our arms by a factor of 100, then our sensitivity would immediately improve by a factor of 100, because we would say kind of a simple assumption would be that we would have this similar kind of hardware to measure the same kind of mirror motion, but the distance across which we are measuring would be increased by a factor of 100. That's very challenging to do, just to build a facility of such a scale. But that is the kind of thing that we are thinking about doing for the next generation of facility. So that's a very good question, a very important question, and one we are.
I am concerning with the increase in LISA NASA, that with an arms of 400 kilometers between the satellites will increase its sensitivity much more than our LIGOs. And I believe it is unfair. I said to Jenne Scanner before that we put all the technology, all the knowledge, and now appear NASA interested from 1915, and without there is no interesting about black hole is still the first merge. Excuse me, it's my personal view. Thanks, Doctor.
Thank you.
Okay, very good. All right, I don't see any more hands up at this point. Maybe we'll have, so we are reaching the limit of our time, but I do see now one more hand up. So Jenny, if it's okay with you, we'll take just one more question and then we'll stop the Q&A. Jen, please go ahead.
I can't hear you yet. If you're asking your question, perhaps you're muted still. I'm still not able to hear. Perhaps you can type your question into the chat, and I or one of the mentors can answer via text. Let's see if I can find the chat window. Oh, maybe he's stepped away.
Looks like he's trying.
Okay. Okay.
Maybe a microphone problem.
Mirrors apart a number of half wavelengths. What frequency? Yes. The laser we use is a 1064 nanometer wavelength laser. It happens to be a neodymium doped YAG type solid state laser, just because those are commercially produced and very, very exquisitely stable. But so our wavelength is 1064 nanometers, and frequency, it turns out, is in the terahertz if you just if you convert from wavelength to frequency using the speed of light. It's quite high frequency. But nanometers, 1,000 nanometers is the wavelength of one wavelength. You're very welcome.
Very good. All right, perfect. Thank you so much. Okay, so I'm sorry, we are out of time at this point. So what I'm going to do at this point is I'm going to stop and restart the recording just for bookkeeping, and then I'll spend just a few minutes on the logistics of our workshop. We may want to take just a moment if you can virtually clap, or thumbs up, or thank our speakers. Both Jenny and Martine gave excellent talks today, and I'm really grateful to them for spending the time to do that. Okay, perfect. So what we'll do now is just a few minutes of housekeeping. So thank you all. Welcome. We're so glad you're here. Thank you for participating in the 2022 Gravitational Wave Open Data Workshop. This is a workshop that's put together mainly by the LIGO, Virgo, and CAGRA collaborations. There's a lot of work that goes into planning these. In particular, there's a team of mentors that works to put this workshop together. You'll meet many of these mentors over the course of the workshop. And if you do, I hope you'll appreciate that they're taking their time to share their expertise with you. So please, above all, remember to thank our mentors. These workshops would not be possible without them. What I'm going to do is share my screen, and I'll walk us through just a couple of logistics about how this workshop is put together. So this year we're trying something new, this hybrid format we've never used before. So our workshop this year has both online and in-person components. Everything about the workshop can be found here on the workshop webpage. So this is on the Gravitational Wave Open Science Center. So that's gwosc.org. So if you go to gwosc.org and go to the workshops tab, you'll find this workshop webpage with all of the information. The structure of the workshop, we've got three main components. There are lectures, which are online, virtual. They can be watched on YouTube live stream, or you can watch recordings after the fact. The lecture schedule is down here in the gray box, and you can see the green buttons if you'd like to watch the YouTube live stream. I will also make recordings available from this page. And then the next component is we have an online course. And so you can see that button here, the online course. That online course is through the Thinkific platform. So the page looks something like this, and you can see workshop number 5, 2022. And if you click that, it should let you into the course, and you can register and then work through the materials that are there. So the course includes some descriptions. We'll try to get links or recordings of the lecture videos uploaded into the course. As you go through it, it'll walk you through how to work with our software tutorials, which is an important component of the course. And so you can access those tutorials through the online course, or you are welcome to get to them directly through the GitHub repo where they live. So again, from the workshop webpage, you've got the Thinkific online course, and you can click the Run Tutorials button to get to the GitHub repo, where you can find all those software tutorials. If you follow the software setup instructions, that should show you several ways to access the material. So all of those things are available and will be available as long as we're able to support them. If you work through the online course, then you will earn a certificate of completion that you should be able to download automatically through the Thinkific. For the tutorials, there's a number of ways to run the software, but in particular, if you're having trouble getting set up, what we tend to recommend for people getting started is to use these online services. So we have the My Binder service, which you can access by clicking the Launch Binder button right here, or you can try Google Colab, which you can use by clicking the button here. These are online cloud-based resources for running the tutorials. They will run in your web browser, so that should be more or less independent of what kind of computer you're on. Of course, if you're brave, you can also try installing the software yourself. There is a LEGO Virgo Cagra computing committee that works very hard to make this software easy, or to try to make it easy to install. And there's instructions, links and instructions here on how to do that. So you're welcome to give that a try as well. And all the tutorials should be able to run in that environment on your computer as well. Finally, the last component is a data challenge. And so again, that data challenge is going to be accessed through the Thinkific platform. So when you're enrolled in the online course, one of the last elements here is the data challenge, and you'll see instructions for how to access that as well. If you are participating in the workshop in May of 2022, you are welcome to submit your data challenge within 1 week from the end of the workshop, and we'll make an effort to collect all those results and to score them. So we do invite you and encourage you to participate in that. It's really the best way for you to try out your gravitational wave data analysis skills and implement all the skills that we're going to learn through this workshop. I mentioned that this workshop is entirely supported by mentors. On the workshop webpage, we do have a Meet the Mentor button. And if you click that, you'll get a page of introductory videos where the mentors, here's Alan, who's been answering a number of questions in the chat today, as well as a long list of mentors who are supporting the workshop. So I do encourage you to take a look and see who these folks are and reach out to them and thank them. The best way to get in touch with the mentors is through our discussion forum. So the discussion forum is at ask.igwin.org. Of course, that's linked from the workshop webpage, so it's hopefully easy to find, easy to remember. And this is a discussion forum where you can come in, post questions, and of course, it's a discussion forum, so anyone can post a question and anyone can post an answer. So our mentors will try to monitor this discussion forum and answer questions as they arise, or if any participants see a question and you would like to share your answer or add to it, you're welcome to contribute to that discussion as well. I think that's it. That's all of my notes. Maybe I'll just share that this is our largest open data workshop yet. We've had over 1,500 people express interest in the workshop. On the live sessions today, we have about 280 people who have joined in either through YouTube live stream or through the Zoom and are watching these sessions right now. So I want to say thank you to everyone for participating. Thank you for your interest in gravitational wave research. Thank you to our mentors and speakers for all the fantastic material. And I'm looking forward to talking with you over the next few days of the workshop. Thank you so much. Have a great day.
Thank you.